harvesting. My name is Frank Edler. I'm coming from Physikalisch-Technische Bundesanstalt in Berlin, from the department Temperature. The main topic of our workshop, Thermoelectric energy harvesting, was a part of the EMRP project, Metrology for energy harvesting, which started about 3 years before and which will end now. But before this really happens, you have the opportunity to learn something about thermoelectric energy harvesting. The key aspect of the EMRP project was metrology. And the key aspect of our workshop will be also metrology. That means we would like to answer the questions how to measure the relevant parameters for thermoelectric materials, which are the Seebeck coefficient, the electrical conductivity, and the thermal conductivity. These three parameters or quantities are used to calculate the so-called figure of merit, which is a mean to compare different thermoelectric materials concerning their efficiency. And therefore, it is very important to measure the three single parameters, Seebeck coefficient and the conductivities, in a traceable way with low uncertainties to have a good mean, as the figure of merit is, to compare the different materials. The measurement of the Seebeck coefficient, as well as the development of reference materials for Seebeck coefficients, will be presented in a talk by Ernst Lenz, coming also from PTB Berlin. The next talk about electrical conductivity will be presented by Bernd Schuhmacher from PTB Braunschweig. And the thermal conductivity will be handled by Ossi Hattala from the Finnish Metrology Institute, MIKES. And last but not least, we will have a talk about nanoscale thermoelectric measurements given by Alex Suna from NPL. But before, I would like to give you a short introduction or an overview about thermoelectric energy harvesting. I would like to do this on basis of these points, which you can see here, starting with a short history review, then dealing with the relevant thermoelectric effects, that means Seebeck effect and Peltier effect. And then we would go starting from thermoelectric pairs via modules, showing some examples, to thermoelectric materials. And at the end, if there's some time, maybe some remarks to thermoelectric generators, which are then the devices which can be produced from the thermoelectric materials. Okay, what is thermoelectricity? We have heard it today often. Thermoelectricity is the direct conversion of heat or temperature difference into electrical or vice versa electricity into heat energy through the two related mechanisms, the Seebeck effect and the Peltier effect. In 1821, Seebeck discovered his effect in a way that he connected two dissimilar metals to each other, which with the two junctions at different temperatures. And in such a circuit, voltage is produced, which can be measured and which was direct proportional to the temperature gradient applied. We'll come to this point later. And some years later, Peltier discovered the reverse effect, which said that in a current in a circuit of two dissimilar wires will heat the junction or cool the junction in dependence on the direction of the current which is flowing through this circuit. Altenkirch was in principle the first who investigated the efficiency of thermoelectric generators and also the performance of coolers, or Peltier coolers. And in principle, his work was the basis of the now common used figure of merit. In the next years, some first applications of thermoelectric generators were investigated and developed, and typical efficiency reached were in the order of about 5%. Over the years, some niche applications with more or less modern materials like semiconductors, the bismuth telluride and others were developed, but there was found more or less a boundary or limit which hinders the development of higher efficient materials, and therefore in the last 2 decades new concepts were developed to find out more efficient thermoelectric materials, and 2 approaches were pursued. One, to use more complex materials, we will see later why, and the other one to use nanoscaled materials, where Alex will tell us something about later. Coming to the 2 effects, starting with the Seebeck effect. If a metal is exposed to a temperature gradient and no current is flowing, then the electrons in this metal behave like a gas. That means they have a higher kinetic energy at the end with a higher temperature and a lower at the end with a low temperature. And therefore, in the sum, they move from the hot end to the cold end, and as a result of this thermodiffusion flow, a potential difference applied, which can be measured as a voltage. And as I mentioned, this voltage is direct proportional to the temperature gradient, and the proportionality factor is the so-called Seebeck coefficient. Considering the Peltier effect, here we have connected also 2 dissimilar wires. Both junctions are at the same temperature, and if we close this circuit and the current is passing through this, then the electrons in, for instance, the material A transport another amount of chemical potential energy than in the material B, and therefore at this junction, when the electrons transfer from A to B, the excess of heat is given to the lattice, and this junction will heat it up. And the other junction, when they transferred from the material where they transport lower energy, then to the material A where they transport higher energy, then they take this difference of the energy from the lattice, and this junction cools down. The heat absorbed or created is direct proportional to the current which is flowing, and you can see the Peltier coefficient is the ratio of heat divided by current. Coming to thermoelectric pairs, in normal use, the thermoelectric pairs are produced from semiconducting materials, because the semiconductors, we will see this later, have a higher Seebeck coefficient than metals. But all what I have said can be transformed also to semiconductors. But nevertheless, even if they have higher Seebeck coefficients, the output in voltage or electric power is only in the range of microvolt or microwatt. And therefore, to get voltages and powers which are usable, practical, usable, it is common to combine single pairs, thermoelectric pairs, to modules by connecting them electrically serial and thermal in parallel, and then you get such thermoelectric modules. As an example, you can see here some parameters of a thermoelectric module from company HiZ Technology, which have an output power of 19 watt by using 78 pairs of bismuth telluride as thermoelectric materials and applying a temperature difference of 200 K. The efficiency you can see here is in principle in the same order like the efficiency of the first generators developed in the beginning of the 20th century. Thermoelectric materials have some advantages and disadvantages. You can see a list of advantages. They are noiseless, wearless, and maintenance-free, and because there are no moving parts, they have a high lifetime. They are free, scalable, cascadable, and what it means we will see at the end of my talk. That means in principle that we can use a large temperature gradient. And the disadvantage of thermoelectric materials that you can see here is that is the only moderate efficiency of about 10 to 20% of the Carnot factor, which you can see here. And that is the reason that only a few applications of commercial thermoelectric generators are known. But of course, there are applications, and some examples you can see here, because we have nearly everywhere in natural or man-made environment temperature differences which can be used for transforming to energy. For instance, the exhaust emission at cars is used for different from different producers of cars. Then we have unwanted heat during waste combustion. We use the Peltier effect, that means a reverse Seebeck effect for cooling photodetectors or other electronic parts. Produce a power of 120 watt and has an efficiency of about 6.3% by using these materials here, lead telluride and a combination of lead and antimonite, germanium and silver. But it's not necessary to go into space. You find also applications in the near environmental. For instance, here such a watch by using the body heat. Don't ask what happened if you have a hot summer. Maybe the owner of this watch has another watch to use. Then, of course, we have applications for self-sustaining sensors. Company Micropelt constructs such sensors. And for instance, the T-light is here in this example used to recharge a mobile phone. But what is the similarity of all these examples? And you know it, I think, that is a low thermoelectric efficiency. And from this reason, I would now come to the figure of merit, as the T values. You can see the three thermoelectric properties of thermoelectric materials enter this formula: the Seebeck coefficient and the electrical conductivity. For suitable thermoelectric materials, this means these both parameters should be as large as possible, and kappa, the thermal conductivity, should be as low as possible. Unfortunately, it is not possible to modify one of these three parameters separately without changing the others, because they depend on each other. For instance, you can see here the dependence of the Seebeck coefficient and the electrical conductivity from the carrier concentration in a material. Seebeck coefficient is decreasing with increasing carrier concentration, and the conductivity, the electrical conductivity, is increasing. I said increasing, Seebeck is decreasing. So therefore, the question arises which materials can be used to get a high efficiency. The maximum reachable generator efficiency can be calculated by using this formula. You find again the Carnot part of this efficiency, and then the mentioned ZT value. And for instance, I have calculated here some efficiency of different materials with other different materials concerning ZT, and in dependence on the temperature difference. You can see first here the red line, that is the Carnot efficiency. It's of course increasing with increasing temperature difference. Temperature difference is in this direction here, increasing. These three lines are more or less hypothetical and fantastical lines because they correspond to ZT values of 4 to 10. But the pink one here at the bottom, near the bottom, stands for ZT of 1, and that is in the moment, I would say, realistic value for practical applications. So in principle, I have mentioned that we can use metals, insulators, or semiconductors. And I would like to pay your attention on copper in this case. Here, if we compare these material groups, copper is the thermal conductivity. For metals, copper is directly connected with the electrical conductivity via the Wehrmann-Franz law and the Lorentz number. That means in principle, if we increase here the thermal electricity, the thermal conductivity by a suitable method, then also the thermal conductivity will increase, because here the heat transport is caused by the free electrons. In the insulators, the heat transport is more or less dominated by phonons, and for semiconductors we have a mixture. And this mixture is one point where research is applied to reduce, in principle, the thermal conductivity, the whole thermal conductivity, by reducing this part of the thermal conductivity. Here are some classical thermoelectric materials. I would like go further. A suitable thermoelectric material should have a Seebeck coefficient between about 150 and 250 microvolt per Kelvin, a conductivity, electrical conductivity, which is higher than 1000 Siemens per centimeter, and a thermal conductivity, which is lower than 2 watt per meter in Kelvin. At a temperature of 500 K, we could calculate with the bold values here, that means 250 for the Seebeck coefficient, this material would have a ZT value of 1.56. From these data, you can get an impression what is necessary to change, to focus the research on. Another hypothetical situation, if it would be possible to reduce the part of the thermal conductivity of the phonons to 0, then we would have like a metal. Then the Wehrmann-Franz law would be valid, and you can see that for a ZT of 1, a Seebeck coefficient of 156 microvolt per K would be necessary, but there's no metal which has such a high Seebeck coefficient, and therefore other ways have to be gone. And I would like to show you the two main directions of the research concerning thermoelectric materials to increase ZT. Of course, you know it's directed on increasing of S and decreasing of kappa, and SLAC proposed as an optimum thermoelectric material, a material which behave concerning their electrical properties like a crystalline material, but with thermal properties of an amorphous material. He named this phonon glass electron crystal. That is in principle a complex material. As examples, Glasrate and Scatterodite are known, and for instance, this is a typical Scatterodite structure. that is a body-phased structure with these formula units cobalt antimonide at the 8 edges of this lattice. This material has a high power factor. That means it has a high Seebeck coefficient and a high electrical conductivity, but also a relatively high thermal conductivity, and therefore this pure cobalt antimonide is not suitable as thermoelectric material. But if you insert in the voids of the lattice such heavy elements, then the phonon scattering is disturbed and the thermal conductivity can be reduced. So this is in principle one way. The other way is development of nanoscaled materials. There are also in principle two directions. Maybe Alex will tell you something more about. Only short remarks. We have in principle bulk materials which consist of nanoparticles, and the reduction of the thermal conductivity is caused by scattering of the phonons at the grain boundaries of the nanoparticles inside this bulk material. And the other way, really construction, or here is called self-organization systems, so self-construction of superlattice structures made of bismuth telluride and antimony telluride. And in this way, here were calculations performed by Higgs and Dresselhaus. They found that if we have a set T of the corresponding three-dimensional, that means the bulk material of 1, then they found for 2D, that means for thin films of this superlattices, set T values of higher than 2. Nevertheless, on the right graph, you can see a comparison of typical thermoelectric materials, bulk materials, and the corresponding nanostructured materials. For instance, here that is the dotted line is for the typical bulk material, silicium germanium, and the corresponding, in the same color, bold line, red, is the set T value then for the corresponding nanostructured materials. You can see it is a factor of 2, it depends on the temperature, better than the typical bulk material. Maybe we come shortly to thermoelectric generators. The efficiency of thermoelectric generators depends not only on the figure of merit of the used materials, but also on the temperature difference. As larger as the temperature difference, as higher the efficiency. The efficiency, I think we can also go here very fast because it was in the first workshop of a device can be calculated in another way than of this material with the set T value. We have here the simple ratio between the output power and what is going in, and the formulas we have seen here before. Maybe one remark: with this formula you can calculate in principle, if you form the first derivative of the power to the current, the optimum current which is used to reach the maximum electrical power, which depends on the inner resistance of the thermoelectric module or the thermoelectric generator then. Another point which is also important to consider is that the load resistance should be in the same order of quantity like the inner resistance of the thermoelectric generators. Here are some measurements of Rapp et al. They have had a thermoelectric generator with the inner resistance of 3 ohms. And here you can see the curves for the efficiency and the power depending on the load resistance, which is on this X scale. And you can see the maximum is reached here in the region of if there's a fitting of the two resistances. that is only so at the end of such thermoelectric generators by not using such copper connection between the two, the P and the N conductive materials, and in this way you can reduce the number of contact resistances which also enter the inner resistance, and in this way it is also possible to get a higher power output. Similar, it's the situation for the thermal losses here. The first advantage is if you don't use this and this PN construction, you have also the complete or nearly the complete temperature gradient which is applied to the thermoelectric generator. That is the same that you can also use. Here you have some more heat losses during the copper layers which are used to connect the different elements. The thermal resistance of thermoelectric modules play also a role in the efficiency and the power, and here were some calculations and simulations done by Pernau from IPM Fraunhofer, who has calculated the output power and efficiency independence of the length of such pairs and of the cross sections. I said that the efficiency not only depends on the figure of merit of the materials used, but also on the temperature difference. But we have also seen before that different materials have their highest ZT values not in a wide temperature range, but rather in small temperatures. And so it was proposed to combine different thermoelectric materials with different ZT maximum values at different temperatures to increase the usable temperature difference and therefore to increase the efficiency. But we come to another point which is not so known like maybe the figure of merit, and that is the compatibility factor for such a segmentation of thermoelectric generators. It is necessary that the materials used are compatible to each other, and this factor can be calculated according to this formula, and here you can see different materials, and if the factor is larger than 2, then it makes in principle no sense to make such segmented generators to improve efficiency. In this way, another proposal was made to use not a segmented, but a cascaded thermoelectric generators with 2 independent circuits, because now the relative current density can be optimized for each of these circuits concerning on the material. And in this way, you can also increase a little bit the efficiency of generators. So I'm at the end of my talk. We can, in principle, summarize that in the last years, the interest in to increase, especially the ZT values and therefore efficiencies. Improvement of the efficiency can be reached also by combination of different materials, and at the end, in principle, with increased ZT values, the thermoelectrics community needs to start the standardization of their characterization techniques in order to confirm reliable high ZT values and to develop practical systems for real-world applications. So with these words, I would like to finish. And maybe if there's questions, then please don't hesitate. Otherwise, we can also come to our main topics, to the 4 talks concerning the different parameters of thermoelectric materials. Okay, then I would propose that Ernst will continue.
Sie haben alle möglichen Autoren von thermoelektrischen Materialien mit hohem Powerfaktor gezeigt, aber Sie haben das IPHT in Jena gar nicht erwähnt. Dort sind schon vor 20 Jahren wohl die Materialien erprobt worden mit Bismut, Antimon, Tellur, die besonders geeignet sind.
Das tut mir leid. Das habe ich erstens nicht gewusst und zweitens wollte ich jetzt auch absolut keinen Anspruch auf Vollständigkeit bezüglich thermoelektrischer Materialien geben. Das ist eigentlich in dieser kurzen Zeit auch überhaupt nicht möglich.
So, good day, ladies and gentlemen. My name is Ernst Lenz, and I'm also from the PTB, as Frank already introduced and said in the talk before. So, my talk is about metrology for the thermoelectric energy harvesting, or mainly connected to the reference material, which I will also present you during this talk. So, what is the content of my talk? I will give you a short motivation, of course, a very brief version from what has Frank already done with some fundamentals. Then I will introduce you to the used SR5 system to measure the Seebeck coefficient, which the system itself was bought from the Fraunhofer EPM in Freiburg. And I will give you the modification which we applied on the system. And I will also present you some data, first data. And after this, we choose as the first reference material isotan, and I will guide you through the certification process so far. And I will present you the uncertainty budget of the isotan and the ongoing certification of this material, which was certified according to the ISO guide, or which is an ongoing certification according to the ISO guide 35. Then I will come to the semiconducting reference material which we choose, which is bismuth-doped lead telluride. And I will give you also the certification process and the uncertainty budget. In the end, I will conclude my talk in a short resume. And so let's start now. So what is the motivation for this? As Frank already told you, the project energy harvesting itself was because of the lack of reliable and traceable measurements of thermoelectric materials at temperatures higher than 390 K. This lack, of course, makes it very difficult to make a comparison between different products and to decide which product might be the best for your application. Therefore, we have to develop a framework for metrology and, of course, to provide traceable and reliable measurement data and measurement systems, of course, and supply the chosen materials. Therefore, to give you an assessment to the efficiency of energy harvesting technology which were developed during this process. And this will also be pointed out as from Alexandra in the talk afterwards, establishing a metrological link between the macro and the nanoscale in this project of energy harvesting. So every good project has some aims. And what were the aims in the beginning of the project? The aims were, we wanted to have a temperature regime from 300 to 900 Kelvin. And of course, which is obvious, the chosen material should be thermal stable in this temperature regime. And connecting to the ZT value, the so-called dimensionless fixture of merit, we need at least a Seebeck coefficient of 14 microvolts per Kelvin. And altogether, should be easily fabricated, which also includes that should be of low cost. And the measurement system itself and the measurement equipment should be should be due to an easy measurement, because you don't want to have a complex machine. So, but what is the main importance for the industry? These are the aimed relative uncertainties. The aim was to have an uncertainty for the Seebeck coefficient of 2%, and an uncertainty of 0.5% for the electrical conductivity, and an uncertainty for in the temperature of 0.1% and 8% for the thermal conductivity. All of this, of course, in the whole temperature range. Unfortunately, we haven't reached all those goals, but I came to this later. So what is the so-called feature of merit, which was also introduced by Frank before? It's the Seebeck coefficient squared times the electrical conductivity divided by the thermal conductivity times temperature. So if you put all those together, you got a relative uncertainty as goal from below 10%, namely 9%. When I say it in this way, it might be clear that we don't reach this up to now, but we are on our way. So if you want to measure the electrical conductivity in such a big temperature regime or temperature interval, then you need a robust method, and the SR5 is equipped in the version which we use up to now with a so-called Ford terminal method. This means you just need to measure the distance where you get your voltage drop over the sample by applying a current I0 through the sample. And then, of course, you have to measure some geometrical geometries of your sample, like height and width, and the length from the sample itself drops simply out. It's quite easy, it's quite robust, and it works. And if you're lucky, you could reach low uncertainties. Not exactly 0.5%, as I will show you later. So, just a brief words to the Seebeck coefficient, which you heard already. If you apply a temperature gradient on a sample, you have a hot end, you have a cold end, and the kinetic energy of the electrons in the hot end is higher than the kinetic energy of the electrons in the cold end. This leads to a diffusion of electrons, and this creates the so-called thermoelectric voltage, all well known, and you can calculate this by calculating this integral. And if the integral is, if the temperature difference is quite small, or the Seebeck coefficient itself is constant, you can simply drop it out and got this simple equation. And this was all covered long ago by Seebeck himself. So, and basically, this sounds very simple. You practically have to measure the temperature gradient, get the voltage drop, and ready. Unfortunately, it's not that simple at all, because you have always voltage offsets. And to get rid of these voltage offsets, we apply a dynamical measurement method where we measure the voltage drop according to the temperature gradient, which is shown here. Temperature difference, sorry, which is shown here. And then you can calculate the slopes according to the used thermocouple elements which were in use in the thermocouple, so which is here now gold and platinum. So now we have the measurement, we know how to do it, and what might be the right material for reference material. As Frank pointed out, normally you would think of metals. Metals can be produced very easily, very pure, and they have a very high homogeneity, but, which was also pointed out by Frank, they all suffer from a very small Seebeck coefficient, and they therefore rule out. Then there is a big area of alloys, metallic alloys. They can also produce with a very high homogeneity, and at least some of them show a sufficient high Seebeck effect. Therefore, you have only to think of your costs, which are connected with them, and therefore we choose a copper-nickel alloy, the copper-nickel 44 mangan 1. It's also known as isotan. I will refer it later on every time as isotan. But the Seebeck coefficient is, as we will see later, is quite low, but it works. So it's sufficient. It's sufficient from sufficient height. Then we have the big area of semiconductors. Normally, you would say semiconductors. They have a drawback of questionable homogeneity. They have questionable stability, thermal stability. They are really doping sensitive, and which is also connected to the thermal stability. They have a questionable reproducibility, which means simply aging. This all are normally things which you would say to rule them out, but they have the big advantage of a very huge Seebeck effect. We tested various semiconductors and we conclude, or we choose as a possible reference material, or as a reference material which we have finished now, the bismuth-doped lead telluride, which I will also present the certification process later on. So what looks the measurement system we use in practice? It was, as I said already, from Fraunhofer, the SR5. So this is only the control unit, height of 1 meter. We have a vacuum pump. We have a measurement volume. We have a connection. And the measurement volume is evacuated, more or less evacuated, and then filled with an inert gas. We use nitrogen or forming gas at a low pressure of 50 millibar. And of course, we have a cooling system, but this is only because it's on the picture. So just go back. In this measurement volume is an inset. It is connected to the connection system here. And the gauge is surrounded by a coil heater. In the coil heater is a ceramic plate which holds these mounting bays with the thermocouples. I will show it later on. And this is actually, or these are actually pictures from the Type K prototype, or Type K version of the SR5 system. This means that here the thermocouples are Type K thermocouples. And from beneath, these were a ceramic tube which were pressed from beneath against the sample. And all this is in the coil heater, which generates the environment temperature. So this is a more detailed picture. Now the enhanced gold platinum setup. Here you see again the mounting base, now with the sample on the mounting base. The clamps are closed now. And here you can see the ceramic plates which were pressed from beneath against the sample. Each mounting base is equipped with a microheater, so we can switch the thermal gradient across the sample. And here we have the reference junctions, which were shown here. And the temperature of the reference junctions is controlled by calibrated PT100, which makes this all traceable to the SI units. So was it worth to switch from Type K to gold platinum thermocouples? And these are the first data. Actually, the last data we took with the Type K version, and the first data we took with the gold platinum version. And of course, the best measurement we have. And you can see see with the naked eye that the noise on the measurement, according to the type K versions, is higher than the noise on the measurement of the gold with the gold platinum thermocouples. And I like to point out, here we have a small deviation. During the time we did this measurement, which was in January 2012 and December 2011, we thought, all right, this might be because these were two different probes and even from two different sheets of metal. So we thought this might be a material artifact, but bearing this in mind, I'll come back to this point later. So there's also another advantage by switching from type K thermocouples to gold platinum thermocouples. Type K thermocouples have to have a certain size because they are very stiff, and the size is approximately 2 millimeters. And simply by going to gold platinum thermocouples, we could reduce the size more or less to a point size, which has only an extinction of, let's say, 1/3 millimeter. This means reducing the size factor by a factor of 6. This does not mean that also the uncertainty in the length measurement is also reduced by a factor of 6. This is only reduced by a factor of 4 because, let me short, the ceramic tubes were pressed from beneath, and there's a mechanism which holds the ceramic tubes in place, and they can a little bit wiggle. So therefore, it's not a one-to-one reduction due to the reducing of the size. But nevertheless, this reduces the uncertainty in the electrical conductivity. I will give this in more detail, but just to give you just a rough overview to about 5%. Please have in mind, we wanted to have originally 0.5%, but it won't get any better. Then there's a next question. The question was, the thermocouples were pressed from beneath. This means you have a certain uncertainty, or a certain amount of uncertainty. How good is the thermal contact? Then it was, the best thermal contact is when everything is made of one piece. This means we simply spot welded the thermocouples against the sample and performed some measurements. And then we took the same sample and pressed the gold platinum thermocouples against the sample. And as you can see here, is really, really nice agreement. But you can also see here, at a certain temperature, nearly above than 670 K, there's a deviation. And we know this deviation because this is more or less the same deviation we had before. But now we are really, really sure that this is the same sample. So there was something different, which we hadn't already known. So we had to go to a step back and look, how does our measurement system work? And we had a look at the coil heater, and we noticed the coil heater is made of such coils. More or less, here is a schematic sketch of the coil heater and the position of the probe inside of the coil heater. And simply by a little contortion of the coil heater, there might be a variation in the distance to the single coils. So this was only a hint. Let's do some measurements. So we had the data from the spot welded sample, which we agreed very nice. And then we make one run, and then just opened the facility, added a little contortion to the coil heater, and did the next measurement. And as you can see, this exactly reproduces, or more or less exactly reproduces, the measurement before. So we know after this, yeah, we have to really take care about the contortion of the coil heater when we stick it on the measurement facility. So be very carefully with this, and always have in mind, if you have done one measurement with one direction of the coil heater, that the next measurement will be with the same contortion of the coil heater. So after knowing this, we took really good care of the contortion and did with various samples, various measurements, and yeah, with the isotan sample. And as you can see here, they were nearly perfect over each other. And this was in April 2012. And after having those nice measurements, we decided to choose isotan as a reference material. So we bought some isotan, make a singling of some part of the isotan, and here you see the length and the width of one single sample. The length is 25 millimeters, the width is 3 millimeters, and the height is 0.3 millimeters. So this was in April 2012, and since then there is the ongoing process of the certification. The certification for this isotan is according to ISO 35, which is a batch certification. And here you just see the sheet which we which we had cut it out from the purchased isotan. And then we took some samples. In some we took 11 samples in this area to measure if the material is homogeneous enough. And in total, we have 453 samples of this size, I said already. And we made some measurements near 303K. Then we calculate the standard deviation, which amounts to 0.33 microvolts per Kelvin, with a variation, statistical variation of 0.126 microvolts per Kelvin, which gives a relative statistical uncertainty of 0.7%. So we can say this is a real homogeneous material, and we can go on in the certification process. And when you certificate according to ISO guide, you have performed the so-called short-term stability, which means that you have to choose appropriate short-time conditions which may occur during delivering of the samples. We choose minus 25 degrees C, and you have to measure them, of course, in advance and after a certain time of storing the samples under these conditions, and you have to measure them again. And you can see here they fit really nice. And if you just look at the relative deviation, you could, at first hand, you can say no deviation is bigger than 2%. This is nice. But even nicer is, or even more nice is, you can see normally you would expect that they is only deviation according to the mean value, and you can imagine that you might have an offset of 1%, but this is an ongoing investigation, and if there should be an offset, a systematical offset of 1%, then you have only deviation of smaller than 1%. Of course, these measurements were not only done at minus 25 degrees C, they were also done at room temperature, simply storing in the laboratory cabinet, and at and at 50 degrees C. but none of them showed a bigger variation than 2% from the mean value. So this means also the short-term stability is guaranteed. And then we can then it's useful to go on to give the whole uncertainty. Yeah, what you have to do when you want to get the uncertainty, you have to look how is your Seebeck coefficient itself calculated, and actually it's this formula is used. And if you look really sharp at the formula, you see that the difference of the slopes, which is here in the denominator, correspond to the relative to the relative Seebeck coefficient, which is tabulated in an IEC norm, and therefore they cancel simply out. And then you have to choose also some Seebeck coefficient which we took out of the literature, but we will see now afterwards in the uncertainty budget. The uncertainty which comes in according to this one is really small. So the main part of uncertainty comes from the slopes, which then in the simplified formula are standing here. But this formula, this resulting formula for the Seebeck coefficient, has a very nice viewing, because if you now calculate the variance, you have your coefficients here. They're your uncertainty coefficients, sensitivity coefficients, and they all were 1/4, or the coefficient itself is 1/2. And the only thing which you have to calculate, or which you have to calculate then, is the uncertainty of the slopes. So what is the slope? The form of the slope was the voltage drop according to the temperature gradient, and then we calculated the slope. So this means we have a part of the uncertainty according to the linear regression, which we used to calculate the slope. Then we have a part of the uncertainty due to the contact, to the thermal contact of the according to the sample. Then we have the uncertainty according to the voltage measurement, and the uncertainty according to the temperature measurement. Additionally, because we have cancelled the slopes, there comes an uncertainty according to the voltage to the slope difference compared to the tabulated Seebeck coefficients of the gold platinum thermocouples. We call this, or we refer to this as the real or the measured Seebeck coefficient. So now we have all parts of the uncertainty. Here's the formula again, and then we did have a look at the uncertainty. Of course, the linear regression is purely mathematic. So you get your standard uncertainty of 0.31 microvolts per Kelvin. The sensitivity coefficient is, of course, 1. Then we have the contact coefficient, the uncertainty due to the contact of the thermocouples according to the sample, with 0.58 microvolts per Kelvin. Again, the sensitivity coefficient is 1. And then we have a deviation of the real Seebeck coefficient of gold, or better saying gold platinum, according to 0.17 microvolts per Kelvin. Then we have an uncertainty according to the electrical measurement system, which amounts to 2.11 microvolts per Kelvin. And we have an uncertainty according to the temperature difference, according to 0.15 Kelvin. So then we have to calculate the coefficients, the sensitivity coefficients, which stands in front of the uncertainties. and we sum it up, and this all leads to combined uncertainty for the slope of the, according to this, to gold, of 2.21 microvolts per Kelvin. We cannot do this only for gold. We can do this only to also for platinum. I don't go to all of this process. I just give you the result. The result is then 0.89 microvolts per Kelvin, and then we have to sum it up. And as I promised you, the Seebeck coefficient, the uncertainty according to the Seebeck coefficient of gold and platinum are very, very small and contribute only to 0.01 and 0.02 microvolts per Kelvin, which is small, to be honest. And this sums up to a combined uncertainty of 1.42 microvolts per Kelvin for the isotan at a temperature of 825 Kelvin. This gives us a relative uncertainty for the isotan of 5% at this temperature. Or here in numbers, the value of minus 57.2 plus minus 2.8 microvolts per Kelvin. So here's a nice picture. Chosen were 5 samples of isotan. They were all fitted in the third order polynomial, and of course, all data together were also fitted by a third order polynomial, which is the blue line here. And the K2 uncertainty is the light gray value, which you can see here. And this is a really nice result. You can also have a look at the poster outside. It's, yeah, really, really nice. So going back to the electrical conductivity, yeah, the formula I showed you before, going through all the stuff again, do all the uncertainty calculation, calculate the variance, you get the sensitivity coefficients and so on, and doing all this in the uncertainty budget, which is shown here. And you see the biggest issue is clearly the measurement of delta L, which means the distance of the point where the voltage drop is taken, with 502 Siemens per centimeter, which is gives in total to a combined uncertainty of 550.6 Siemens per centimeter, and this leads to a relative uncertainty in the K2 of 5.5%. So these are the measurements, and you see there is the reproducibility is much, much better. So now the semiconducting material, as I have said, we have chosen bismuth doped lead telluride, and as you can see, we recognized an aging effect when the lead telluride is heated above 700 degrees C. So this says to us, don't go that high in temperature because you don't want to have aging effects. But if you want to go to a reference material, you have to guarantee a certain temperature, and over this temperature, and if you're staying beneath this temperature, there is no aging effect. Therefore, we have made a measurement of the bismuth doped lead telluride going up to 660 K, and at least more than 24 hours at temperatures higher than 600 K. And if you just neglect the first run, which is just an annealing run for the surface to get rid of the oxide on the surface, you see that there is no aging effect measurable at this material. So, oh, this is not. this is the sample which we got, and normally there should be a Fraunhofer Institute because Fraunhofer gives us those samples and produced also those samples. We get them from Fraunhofer. Sorry. And just by looking at the size, it's clear the certification according to ISO guide is not possible because simply we don't have enough samples. Because we got one batch consisting of 2 disks. Each disk gives 19 samples. In total, this means 38 samples. And for a batch certification, you need 40 samples if you include the long-term measurements. So therefore, we have to do a piece-wise certification. This means a certification for every piece has to be done. But what I can show you also, or in addition, is the really nice repeatability of the bismuth-doped telluride. And yeah, you can see very high Seebeck coefficient in the chosen temperature range. We did also some measurement according to the storing conditions. In total, we came to that also here we have no higher deviation than 2% from the original value. So this is also nice to have. And then we have the uncertainty budget from the lead telluride, which has now, it's the same procedure as before. So I just want to point out, we have now an uncertainty of 3.99 microvolts per Kelvin. And for the platinum, now we have 3.79 microvolts per Kelvin, which ends up in a combined uncertainty of 2.75 microvolts per Kelvin and leads in final to the K2 uncertainty of 2.4%. So which is really near to the wanted aim at the beginning from the Seebeck coefficient. Here you see again the nice curve with the light gray area of the K2 value, and yeah, it's also a very nice picture and looks very good. Also, we have measured here the electrical conductivity, but we just have given the experimental uncertainty because we are not able to build up an uncertainty budget for this specific material. So in total, this means I have shown you how we reach isoton as reference material for the Seebeck coefficient in a batch certification with a relative uncertainty according to K2 from 8 to 5% in the temperature regime from 300 to 860 K. And I also showed you the bismuth-doped lead telluride as reference material for Seebeck coefficient, now in a piecewise certification with a relative uncertainty, also K2, from 3.7 to 2.5%. And now in a reduced temperature regime from 300 to 650 K. And both reference material should be ready and available at the end of this year. So, thank you for your attention. And yeah, I expect some questions, or hopefully you understand everything. Thank you. Yeah.
Do you have any plan to have a P-type Seebeck reference material?
No, we just looked at nice materials, and it was an N-type, so we never thought about a P-type, but So we have now 2 reference materials, but of course we can measure also with this facility p-type materials, but there was no condition to, or no constraint to do a p-type material, at least not to my knowledge.
Further questions? Okay.
Oh.
Okay, I'm not an expert in this field, but I ask myself, who are the customers of such a measurement for this reference material?
The customers will be, of course, people who are, so there are, the customers for the reference material will be, of course, everybody who provides such measurement facilities, just to calibrate them. Of course, who is interested in measuring the systems, all people who develop thermoelectric materials. Mm-hmm. So, yeah, I hope this answers your question.
Yes, thank you.
No more questions? Okay, thank you. Okay, good afternoon, gentlemen. Well, what I would like to talk about now is a little bit about the measurement of the electrical conductivity, where we have some different approaches here in PTB Braunschweig. And I will show you some different methods. One is the established method for conductivity of metallic materials that we are using for several years in our laboratory. And then I will show you some of the advantages of this old method and some advantages of the Van der Pauw method. And I will give a few words on the requirements for the instrumentation that you need to do the calibration of electrical conductivity with smaller uncertainties. Now, in general, what do we understand under conductivity? Conductivity is a material property that depends on the number of free electrons and their mobility. And it's usually this quite simple formula from the first semester of your physics studies, where the conductivity is the number of electrons, the electronic charge, and the mobility. And experimentally, you can determine the conductivity by measuring the resistance of a metallic sheet, R, and then, as Ernst has already shown, you need the dimensions, the width, the thickness, and the length of the material in order to calculate the conductivity. The principle I have shown in this diagram, which is some 10 years old, where we had the first EU project concerning the difference between AC and DC conductivity of metals. In that case, usually we have bar-shaped pieces of metal where we pass a current through, and we have 2 knife-edge electrodes in a certain distance called length here. And if we know the cross-section area, as I told you, we can simply calculate the conductivity of the bulk material. There are some boundary conditions. One is that these knife-edge electrodes have to be perpendicularly to the cross-section of the metallic bar, and also the current must be of a size that it's high enough to have a reasonable voltage, but not too high to get some effects that the current is pushed to the edge of the material so that the current is even homogeneously distributed through through the metal bar. And one of the main constraints of the whole thing is that all these dimensions that you have here, length, width, cross-section area, that they are constant over the whole sample, which in practice is not the case. So you have some inhomogeneities, you have some variances in the dimensions. We once had a customer who was very proud and he had polished his standards before sending them to PTB. But usually if you do polishing afterwards, you don't have flat surfaces, but you have some curved surface. So this gives some big errors in the conductivity measurement. So in practice, probably you have seen it outside. These are these electrodes that we built during this project, which was a main advantage to the method we used before, where we had some point contacts on the sample. And every time if we did make a calibration, then we would have to search really with the microscope where was the indentation of this point contact in order to determine the length. So having these special knife edge electrodes precisely machined with a certain distance that we can calibrate with our length people, then we have a very fixed distance of the electrodes. And so this reduced one uncertainty component dramatically and helped very much in order to do the measurements in a more effective way. But still it remains, you have to keep in mind that you have to measure the thickness over the whole length of the sample. And then you have here the current clamps where the current is passed in. And then some standard requires that there is a certain distance between the point where the current is passed in and where you take the voltage drop. And a rule of thumb is approximately that this distance here should be greater than the width of the sample in order to get a homogeneous distribution of the current in the sample. The measurement range that we currently cover for metals goes from 0.5 megasiemens per meter to 65 megasiemens per meter. And for those who might have heard it, there is something that's called IACS. It's the International Annealed Copper Scale. In that case, it would range from 1% to 110%, and 100% IACS is the conductivity of pure copper. And for metals, because they are so good conducting, we need high currents, and we need a current transducer or shunt to measure the current, and a nanovoltmeter, because the voltage drop that you really have to measure is below 1 millivolt. And this requires that you use a nanovoltmeter. So here's the measurement setup that we are using for such measurements. And this was the special variation that we needed now in the project to do a verification of our calibration method by measuring an isotan strip with this method here. Here's the current source, the current transducer to measure the current. Oops, sorry. And the output signal of this current transducer is measured with a voltmeter, because this gives something of 10 volts for the nominal current. And this is the nanovoltmeter connected here to this block with the knife edge electrodes. Typical sources of error, I have already mentioned a few. One is the determination of the geometry. Then, of course, the imperfection of the geometry, the flatness, and some variation, and also voids or damages and dents and something. One thing is also the imperfect contact of the knives. If it's somehow distorted or tilted, this can give some cosine errors. And of course, if we are talking about voltage measurements on that level, thermoelectric voltages are an issue, which you can overcome by current reversal, because the thermoelectric voltages usually stay constant, and if you reverse the voltage, you can eliminate it. But this is not the whole truth, because these thermoelectric voltages are not necessarily stable over time. Now there's an alternative method to this 4-terminal method, which also is a 4-terminal method, but in a different geometry. It's the Van der Pau method. The principle is quite easy. Okay, I made here rectangular shapes, but in the original theorem of Van der Pau, you can have a deliberately shaped sample of constant thickness, and then you only need 4 point contacts, 2 to pass a current in, and 2 to measure a voltage drop. And so with the ratio of voltage to current, you can estimate a resistance value, which is usually called R1, and then you can swap the whole thing by 90 degrees and do the same, again, current, voltage on the opposite side, and you get a second resistance value. And oops, I missed something. Okay, and from these 2 resistance measurement, hopefully I have somewhere the formula, you can calculate from the Van der Pau equation, you can easily derive the conductivity of the material. So this is how this measurement setup would look in practice. Again, you have a current source. You have the conductivity sample in some sort of sample holder with some contacts on the edges. You need some switching for the current reversal and some switching to switch the voltages and currents in a way that you could actually measure 4 resistance values if you would go along the sample here one way. And of course, you need the nanovoltmeter to measure the voltages, and also via some reference resistor to measure the actual value of the current that you pass through the sample. So for one measurement, you would pass in the current here in contact 1, get it out in contact 2, and measure the voltage between 3 and 4. But what happens there? It's one of the constraints of the Van der Pau method. It requires point contacts. And if you pass a reasonably high or low current through a very small area, then you have a quite high contact resistance and you get local heating in these corners, which is not so much of a problem at first sight. But if you make the second measurement, then you see that one of these heated spots becomes now a voltage contact. And a heated spot means, in that case, at that place, you have some drift in temperature, and hence you get some drift in the thermoelectric voltage. So that means between the switching, sometimes you have to wait a little bit for the temperature to stabilize again, because usually it's only a few tenths of a Kelvin, but since we are talking about thermoelectric material, it may give rise to rather high thermal voltages. There are some other constraints to the Van der Pau measurement. You measure 2 resistance values, and if you have an ideal quadratic sample, you would expect that both resistance values are the same. But in practice, this is rarely the case, but the Van der Pau theory gives a correction factor, so you have to determine the ratio of these 2 resistance, and you get some correction factor for the final value. Okay, also here we have typical sources of error. Mainly one is also the determination of the geometry, but this is the advantage of the Van der Pau method. You do not have to measure all the geometry parameters of your sample. You need only the thickness. But since this is typically the smallest of the dimensions, the error here is the biggest. And also you have to deal with the imperfect geometry of the thickness. Both surfaces have to be parallel and flat and should be flawless. The other thing is that you hardly can get any perfect point contacts. Usually you have some flat contacts there, or you have very small point contacts with the heating effects I described earlier. And the same with all voltage measurements. Again, the thermoelectric voltages may spoil the party. So there are some other corrections that can be applied with regard to this contact points. The method requires ideal point contacts, but as I told you, there is a conflict. Small contacts have high contact resistance and self-heating. So if you have large contacts, you have less heating, but you need a correction for the contact size. And also there, the theory gives some estimate for the additional uncertainty of the size of the contact, where the actual diameter of the contact, the ratio of the actual contact to the circumference of the sample is a factor beta, and with that formula you can also calculate some correction factor or additional uncertainty contribution for the uncertainty of the Van der Pau measurement. Okay, finally, for such a measurement, you need to have an uncertainty budget, and you can use some linear approximation for this, because the Van der Pau equation is an equation. I'm really confused that I really have missed to present you this equation, sorry for that. But this is some linear approximation for the Van der Pau equation, where you have the 4 resistance values if you go one time around such a quadratic probe, and you just need pi and some mathematical constants and the thickness of the sample. And we did this now in the project for an isotan sample with 10 millimeter size, 10 by 10 millimeter in square, and passing a current of 30 milliamps through it. This produced a voltage of around 6.5 microvolts. And we came to a sigma value of 2.02 megasiemens per meter and a relative uncertainty of the order of 1%. And you can see here from the budget, the main contribution is from the thickness measurement, and also the small voltage gives a significant influence in the total uncertainty for the conductivity. So we did this also for isotan, which is planned to be used as a reference material for thermoelectric materials. And we did it on a 10 by 10 millimeter quadratic plate with 0.3, 0.5, and 1 millimeter thickness in a temperature range between room temperature and 400 degrees. We need a current source with a few microamperes or milliamperes for this lower conducting materials. A set of contacts, now preferably needle contacts or clamped contacts, and also, again, the nanovolt meter. And here are some stages where we went through with our measurement setup for the conductivity. The first one was to have the sample just being held by some special point contacts, which were conic and would fit in one way, keep the sample and also give electric contact to it. The second one is that one that you can see outside, close to my poster, where we have some clamps. This is the first version where we had brass clamps. Now we exchanged it to pure copper clamps, which had some advantage from the contact resistance. And this setup also was possible to do some heating up to 600 Kelvin. This is the measurement instrumentation used for this. We had the nanovolt meter, a current source, and 2 scanners, one to switch the currents to this sample and one to switch the nanovolt meter to the opposite things to measure the voltage drops on the opposite sides of the sample. And this scanner is a rather specialized one, Alan Schaller, who worked in the project for us, did this development here, because the commercial ones have the problem that sometimes you get rise to high thermoelectric voltages in the relay switching. So the idea was to have the relays thermally shielded by some massive aluminium blocks, and so you get a thermal equalization around the relays. And they are all built in a way that we have 2 bus bars and that we can connect several channels to the multimeter. And measurements showed that we could get a leakage resistance greater than 100 gig ohm, and the uncompensated thermoelectric voltages of this scanner are far less than 50 nanovolts. And this is the measurement results that we obtained on that isotan sample. It's the example for the 1 millimeter sample. You can see we have covered the range from 300 to 600 Kelvin. And okay, the value is around 2 megasiemens per meter. And you see some slight increase with higher temperature. And these are the type A error bars, which are a bit smaller than the total uncertainty. And an essential point was then also the validation of the Van der Pau method. We used, as I showed in the picture at the beginning, our standard bar method to determine the conductivity of the same batch of isotan that we used also for the Van der Pau method. And within the uncertainty, you see that the values more or less agree. So we can say the Van der Pau method is at least within its uncertainty level of about 1% as accurate as our standard method. Okay, to summarize, conductivity of materials is an important parameter, but the disadvantage or requirement is that you always have to do some dimensional measurements, which can be problematic, and also that you have to take care of perfect geometry. The advantage of the Van der Pau method is you only need to measure one dimensional parameter precisely. And I have showed you a proposal for the measurement setup. And okay, we also could show that the expanded uncertainty of this new Van der Pau method agrees well with those of our reference method. Okay, thank you very much. Don't ask for the Van der Pau equation. Okay.
I mean, in the industry, when they use Van der Pau, they used to have, well, they still have microstructures they can pattern on a sample. Would it not be better in terms of uncertainty to have a patterned microstructures, Van der Pau, Greek cross, or like the semiconductors industry use, rather than trying to have wedge or point probe system?
It's difficult. Well, with such things like the Greek cross method or so, you can have, or we did try some in this way to overcome some of the disadvantages of this point contact method. If you look carefully here at this picture, you can see this was one sample where we put in some slits to get some sort of cloverleaf structure, which is then similar to the Greek cross effect, but it's easier to manufacture. And with such a method, okay, you reduce the effective area that you investigate, but you get a little bit rid of these point contact problems. You're right. So having some structure may help in improving the method. But on the other hand, on the cost that you still, again, reduce a little bit the size of your sample that you investigate, but and necessarily you then get also smaller voltages. And so it's, you have to check what you gain and what you lose with such microstructures. But certainly you're right, structuring helps